Let's take a look at some pro tips when using the limit comparison test. So step number one, you got to choose a comparison series. And that comparison series, what's yours look like? Does it look geometric? Does it look like a p-series? You choose those things because they're very easy to compare to. And it's also easy to establish the convergence or divergence to both of those type of series. Okay. Discuss the convergence of that new series. Does it converge? Does it diverge? Okay, so we've established that. Now set up your limit like this, our new one over our known one. And if this limit is finite and positive, then they have the same behavior. If it's not, you don't know anything, you got to choose a different test, okay? So whenever you go to find a comparison series, you're basically looking at the most dominant terms, highest powers here. So for example, we've looked at this one already. Highest powers here, well, you got 2 to the n on top, you got 3 to the n on the bottom. That's what you should be comparing that to. And, maybe you put this all to the same power, which of course that one, 2/3, that's less than 1. This is a convergent geometric series. Okay, all right then. Or maybe we look at something like this. Look at this, this is crazy. But look at the dominant terms. Dominant terms, the highest power on the top is this n squared up here, and the highest power on the denominator is n to the fifth, but you're taking the square root of it, right? So just get rid of all the other stuff and then see if you can simplify that. This down in the bottom is 5/2 power, and then subtract your exponents there, something like that, and you have 2 over n to the 1/2. 1/2 is smaller than 1. So let's see, p series, right? If you're smaller than 1, then this thing is going to diverge. It's got to be bigger than 1, bigger than that harmonic one. Okay, so here, let's try another one here. Determine whether the series n equals 1 to infinity, 1 over 2 plus the square root of n converges or diverges. All right, so I can see that the dominant thing in this is just the variable term. It's the only thing that's going to change. That is 1 over n to the 1/2 power, p series. Smaller than 1, it should diverge. Okay, so let's see if we can prove that it diverges. Let me scroll through all of this stuff, and I don't have an extra page. I'm probably going to need it, so I'll put 1. Okay, good. Okay, so first of all, are these terms greater than 0? Yeah, they're positive. I'm taking the square root of something, and that's the square root symbol. That is the principal square root, so always positive number, blah, blah, blah. Sure, they're positive. What about the nth term? Well, the nth term, this is the only thing that's enlarging, and that stays the same. So yeah, those are going to 0. So no conclusion there, no useful conclusion. All right. So what are we going to compare it to? We're going to compare this thing to the series n equals 1 to infinity, 1 over the square root of n, or if you prefer, scribble, 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 n to the 1/2 power. That is a p series. P is equal to 1/2, which is smaller than 1, so this guy is going to totally diverge. Divergent p series. If you're going to do the direct comparison test, you would have to show that ours is bigger than this, but since we're using the limit comparison test, we just take the ratio and see if the limit of that ratio is finite and positive. We're just basically seeing, are they finite multiples of each other ultimately. So we're going to take the limit as n goes to infinity. We take ours on top as 1 over 2 plus the square root of n over the new one, 1 over the square root of n. Fix your complex fraction, the limit as n goes to infinity. 1 over 2 plus, and you know what? I know what's going to happen. The square root of n, that's not the eraser. The square root of n that is on the bottom right here is just going to shoot up to the top here when I multiply by the reciprocal. So I have the square root of n over 2 plus the square root of n. Okay. Sticking in infinity, you got infinity over infinity. It's L'Hopitalable. Or I can see that this thing is going to go to 1 if we look at the powers. If you don't believe me, that's okay. We can go ahead and use L'Hopital's rule, right? You wanna? So this one goes to infinity over infinity, which is L'Hopitalable. Hey, we haven't really done that in a long time. We've kind of just avoided doing L'Hopital's rule, but I'm going to do it this time because it's fun. All right, what is the derivative of n to the 1/2 power? It is 1/2 n to the negative 1/2 power. And then the same thing is going to happen. What are you doing? Same thing is going to happen on the bottom because the derivative of 2 is equal to 0. So I have another 1/2 n to the negative 1/2 power. Everything cancels. I get 1, which is finite and positive. And the keyboard pops up because why not? Which is finite and positive. All right, what does that mean? Well, that means that they both do the same thing. They have the same behavior. This guy diverges, so ours must also diverge. Let's write it up, shall we? Since, let's see, what is ours? Ours is 1 over 2 plus the square root of n is greater than 0, and 1 over the square root of n is greater than 0 for n is greater than or equal to 1. And our limit, let's establish that, n is, as n approaches infinity, of 1 over 2 plus the square root of n. That's what that says. Don't believe me? Okay, I'll rewrite it. Over 1 over the square root of n is equal to 1, which is finite and positive. Okay, there we go. Then our conclusion is then the limit, no, not the limit, just write the series, come on. From n equals 1 to infinity of 1 over 2 plus the square root of n diverges since the one that we compared it to, n equals 1 to infinity of 1 over the square root of n, is a divergent p-series. Right, your p is equal to 1/2. Okay, there you go. That should be enough. That's the limit comparison test for you.